Okay, today's lesson, we're going to start chapter 8, which is on logarithms. So chapter 7 was exponents, and we got to a point where we had trouble solving exponents because we got to a situation something like 2 to the x equals 5, and we can't change the 5 to be 2 to the power of something else. So this is where logs come into play. And the first definition, or the first thing you want to think about with a logarithm, is it's just an inverse of an exponential graph. So in terms of a graph, remember when we do inverses, that's a diagonal reflection, or in other words, we just trade our x and y coordinates. So if we have y equals 2 to the x and we trade those around, we would get the inverse. So that means every coordinate, so this one is at 0, 1, on the log graph it now becomes 1, 0. And so on. So every other coordinate just flip-flops its location. So in terms of what a log function is, that's really how we want to treat this, is because they're an inverse, so we get this diagonal reflection. So in terms of an equation like y equals 2x, we would trade the x and y around, and we can't solve that. X equals 2 to the y can't be solved. So what we do is we come up with a log. So x equals 2 to the y. If we solve that for y, we get y equals log 2 of x. So the inverse graph is the exact same thing. So the trick is, in order to change an exponent into a log, is we take the base, keep the base the same, and then we trade our x and y. We kind of do a bit of a crisscross. So if we look at this 5 to the 3, we would write that as log 5, so the 5 base number stays the same, and then we crisscross. So the 125 goes on that side, and the 3 would go on the other. So log base 5 of 125 equals 3 is the exact same thing as 5 cubed equals 125. So what you're basically saying is the base number of your log, 5 to the what, equals 125, and then it would be 3. So another note to be aware of, if we say log base 10, that is our sort of our standard log. So normally we just write it as log 5. That's implying that we have base 10. And on your calculator, that's what the log button is. It's actually log of base 10. So you got to be aware of that when you're working with those. Okay, so let's go through the graphs and kind of work backwards a little bit here. So for our regular graph, our regular exponential graph, so y equals 2 to the x. I got the x not done right. So 2 to the power of x, we have a domain of XER. Our range would be greater than 0. We have no x-intercepts, and our y-intercept would be at 1, and our asymptote would be the x-axis, or when y is 0. So in this kind of graph, all of our exponential values are above 0. So now if we were to draw our log graph, so remember it's the inverse, so that would be the diagonal reflections, that would be where our reflection line is. And then all of our coordinates trade. So this 0, 1 will now become 1, 0. And another one, so this other one's at 2, 4. It'll now become at 4, 2. And we'd end up getting our graph looking something like that. So in this case, if we go through domain and range, our domain now is any number greater than 0. Our y is YER. Our x-intercept now is at 1, 0. We have no y-intercepts. And our asymptote would be at the line x equals 0, so we get a vertical asymptote. So you can see, because they're inverses, all of these things just trade. Our domain and range just flip-flop, our x-intercepts and y-intercepts kind of flip-flop, and our asymptotes goes from x to 0, or x to y. Okay, so let's do a little bit of practicing. So we're going to use this formula to trade back and forth. So 3 to the 4th equals 81. As a log, we'd write that as log base 3 of 81 equals 4. So that means 3 to the power of what equals 4, which is 81, so that's good. This next one would be log base 36 of 6 equals a half. And that's true, because remember 36 to the half, that's like square root of 36, so square root of 36 is 6, that's true. And let's switch these ones the other way around, so that'll be 5 to the 3 equals 125. So yeah, remember your base number is the same, and then crisscross your 3 and the 125 in this case. This one, remember, it's base 10, so you'd have 10 to the power of 4 equals 10,000. And let's actually solve, in this case, all these ones. So we'd have 2 to the x equals 32. And we can solve these like we did before. Change the 32 to be 2 to the 5. So that means x equals 5. Okay, the next one, we'd have 100 to the x equals 10. So we change the 100 to be 10 to the 2, so 10 squared. And that'd be like 10 to the 1, so we'd have 2x equals 1, so that means x would be 1/2. The next one, we'd have 3 to the x equals root 27. Change those to the same base. So 27 would be 3 cubed, so the root would just be square root, which is 1/2. So we'd have, in this case, x would equal 3/2. The next one, we got 4 to the 3 equals x. Well, 4 to the 3 is 64. X cubed equals 125. This one we can actually solve. How do we do get rid of a cube root? You cube root it. So the cube root of 125 is 5. And the last one, we have 10 to the x equals 0.01. So 0.01 would be 10 to the -2. So in this case, we get -2. And that's it. So understanding, first of all, what a log is being just the inverse. And then after that, just converting things back and forth to rewrite them in an exponential form and solving it. And that's all for this lesson.